Welcome everyone. In this video, we are going to discuss inference strategies for a multiple linear regression model, so a model with more than one explanatory variable. In this case, we will create a model from the empty cars dataset, which consists of fuel consumption data, as well as 10 features of automobile design and performance overview for 32 automobiles. Here, I am looking at a head of this dataset and examining features such as MPG, which is miles per US gallon, the HP variable, which is gross horsepower, and WT variable, which is the weight in 1,000 pounds. We will next construct a multiple linear regression model with these parameters. Here, I am constructing a multiple linear regression model where MPG, or miles per gallon, is the outcome, and the HP and WT variables, which are the horsepower and the weight attributes, are the explanatory variables. I am next viewing summary of this model and the analysis of variance output, which is the AOV function. We will utilize these next for computing variance inference methods in the subsequent slides. Here, I'm estimating the standard error of the multiple linear regression model, where k represents the number of features or explanatory variables, while n represents the sample size. We have n minus k minus 1 here since we are losing an additional k plus 1 degrees of freedom when estimating a new model coefficient. So, to compute the standard error of the model, we are dividing the sum of squares errors as retrieved from the analysis of variance model by n minus k minus 1, and then taking the square root of the quotient. We can see that the standard error is 2.593. Next, we are computing the individual t-tests for each coefficient in the multiple linear regression model. For computing the test statistic, I'm dividing the coefficient or the beta estimate by the standard error of the estimate. We are performing this operation for both the horsepower and the weight estimates. The test statistic for the horsepower HP variable is minus 3.518, while the test statistic for the weight estimate or attribute is minus 6.129. We can consider extending this framework to compute individual p-values if the assumptions of normality hold, for example. Here we are computing the confidence intervals for coefficients in a multiple linear regression model for each of the horsepower and the weight attributes. We are computing the 95% confidence interval for each coefficient by accordingly adjusting the beta coefficient estimate by the product of the critical value, which is 2.05, by the standard error of each estimate. We can observe that the 95% confidence interval for the horsepower coefficient ranges from minus 0.05028 and minus 0.01326, while the coefficient for the weight attribute ranges from minus 5.175 to minus 2.581. In this analysis, we are exploring the analysis of variance, ANOVA model output, by first computing the mean squares model and the mean squares error. We are computing the model mean squares model by dividing the sum of squares by k, which is 2 in our case since we are predicting two predictors. The sum of squares model will be the sum of the model squares corresponding to the horsepower and the weight attributes. The mean squares model is 465.4997. The mean squares error will be the sum of squares error divided by n minus k minus 1, which in this case will be 29. The mean squares error is therefore 6.7258. Next, we are computing the F statistic, which represents the ratio of the variances of the model and the error term. In this case, the mean squares model from the previous computation is 465.4997, while the mean squares error is 6.7258. The F statistic is therefore 69.2110. We can compute a p-value corresponding to the test statistic given that conditions such as normality hold using an F distribution with k, 2, and n minus k minus 1 being 29 degrees of freedom. Next, here we are computing the coefficient of determination, or R squared. This corresponds to the amount of variation in the response variable that is accounted for by the explanatory variables. The R squared value corresponds to the ratio of the sum of squares model to the sum of squares total and comes out to be 0.8268. This result suggests that about 83% of the variation in the miles per gallon attribute is accounted for by the horsepower and the weight variables. One challenge with the coefficient of determination is that it will always be the case that an addition of a new variable will increase the variability accounted for by the model. To correctly disassociate that variability into useful or true variability, we can compute the adjusted R squared. This adjusted R squared metric adjusts for the number of variables added in the model. In this case, the R squared value is 0.8148, which suggests that about 81% of the variability in the MPG outcome is captured by the horsepower and the weight attributes. This is all for this video. Thank you everyone for listening, and see you all in the next video.